Get ready to watch students become passionate about physics. Get ready to witness a teacher that doesn't lecture or give all of the answers. Get ready to observe students building and evaluating scientific models. Get ready to hear students participating in scientific discourse. Get ready to watch a class of 8th grade students successfully explore, explain, and apply their knowledge of high school physical science in a real-world situation. We are currently working on a unit on motion. The standard for this unit asks students to obtain, evaluate, and communicate information about motion. More specifically, students are expected to plan and carry out an investigation to analyze the motion of an object using mathematical and graphical models, a concept that is extremely challenging for students to comprehend. You will see a diverse set of students. Some are special ed, some are ESOL, some are gifted, some are 504. Because of their wide range of abilities, there are many scaffolds that you will see being used. Some students are holding graphic organizers to help organize their ideas prior to our class discussion. This allows the students to anticipate what questions might be asked of them and how they might answer the questions. It also gives them more time to think of possible questions that they could ask the group. You will also see students with vocabulary graphic organizers. These are for my Level 1 ESOL students who speak very little English. They are provided with some simple words that will be commonly heard in the class discussion. Lastly, you will see students holding index cards. These students are given a few different questions that they could ask in the class discussion. Since the questions come from me and no one knows where they got this index card, it gives my struggling students the confidence that they need to become a more active part of our class discussion. Our unit began when students designed a lab to answer the question, how does the velocity of a car change when it travels in different directions? To complete this lab, students were given the car and a lab question. Alone, they created procedures and collected and analyzed their data. Students used constant velocity cars to measure the car's change in position with respect to time. After they graphed and analyzed their data, they created a whiteboard with a final claim, data, and justification. They presented their whiteboards to me and their classmates. To conclude the lab, students wrote a final lab conclusion. In this lab, students learned that the slope of the line of a position versus time graph indicates the velocity of the car, and that changing the direction of the car will change its velocity. Next, students used motion detectors to explore how their movements are related to a position versus time graph. Using a motion detector in their own bodies, they tried to move to match the position versus time graph shown on the panel board. This activity really helps them to relate a graph, which many of them have a hard time reading, to real-life movement, and you might notice that they had a lot of fun doing it. This brings us to today's lesson. Students studied the position versus time graph for 2 cyclists. After making sense of the graph, they created their own argument as to whether or not the cyclists have the same velocity at 5 seconds and what happens at the intersection of the 2 lines. We're about to see a both small and large group class discussion where excited students will defend their boards and question their peers' opinions as we come to a class consensus. Because after the bell rang yesterday, the argument about velocity echoed down the 8th grade hallway.
Good morning, ladies and gentlemen. Happy Friday. Do you have your warm-ups finished? Yes. Yes, you're done? So we have 2 questions that we're looking at. Question number 1, we're looking at this graph right here. Are A and B ever going the same velocity? And question number 2, what is happening at the intersection of the 2 lines? I would like you to turn to your elbow buddy and share your answer to question number 1. Go. And finish your conversation in 5, 4, 3, 2, 1. All right, we're going to have someone share for us. So the question is, are their velocities ever the same?
They're not the same.
They're not the same. All right, and how did you and your elbow buddy know that? Pardon me? The slopes of the graph are different. Did anybody come up with a different answer? We're all on the same page? All right, then let's go with question number 2. Looking at the 5-second mark, I think we might have a little bit of controversy here, that's okay. So looking at this 5-second mark where the lines intersect, you're now going to tell your face partner across from you, telling your face partner you can work as a group of 3. What is happening at the intersection of the lines? Ready? Go. You're still a face partner. All right, and finish your conversation in 5, 4, 3, 2, 1. Let's see who's going to share. Zeke.
They're side by side.
You said side by side, and did your elbow buddy agree with you?
No.
He did not agree with you. So correct me if I'm wrong, we ended in kind of a heated controversy yesterday, yes?
Yeah.
So argument. So you said side by side, so does that look like this? Side by side. And so if this is cyclist B and this is cyclist A, you think they look like this? And how does that relate to the graph? How does that relate to the graph? So you're saying when they're the same distance from where I start, the origin like here, 0? So when they're the same distance away, that's when they have this intersection? All right, what did your partner say?
Oh, I said they go like this.
And how can they go like this without crashing into each other?
Oh, they're on like a bridge.
So is yours kind of like this?
Yeah.
Right there? Our goal for today is to come to a class consensus. So think in your head, how will I know if I am successful by the end of the period today? What will success look like if we can come to a class consensus? Turn to your elbow buddy and discuss. Go. Okay, by raising your hand, what will success feel like at the end of the period? What will it look like? Sabrina.
We all agree on one point.
All right, so one way we will be successful is when we can all agree. All right. What else? Catherine.
When we'll all understand the idea.
So not just that you agree with the idea, but that you're confident?
Yeah.
Okay, so you're confident and you know your idea is correct? Mm-hmm. All right. All agree. Confident / know we are correct. And what are we confident and correct about? About what? We're agree about what? We're confident about what? Don't be afraid.
So velocities are never equal.
All right, velocities equal. Anything else? The intersection point of the line. So I'm going to draw the graph. Position, time, and at 5 seconds. So at the end of the period, success will look and feel, we will feel confident about knowing the correct answer. Are the velocities the same, and what happens at the intersection in 5 seconds? And we will be able to explain that in detail. Do you agree with that?
Yeah.
All right, let's make it happen. Team, grab your whiteboard, go.
It's Harwood.
Wait.
What if A is going, then B passes right in front of him, and then it forms the X?
So like A goes first and then B goes next?
Yeah. Because then it isn't stopping.
He says no because it's the same time.
I know, but like if they stop, there'd be a crash. That's why you can't stay the same speed if you run into each other.
Look at how the line is shaped. Like B is technically slower, is going slower than A, because it makes sense when you think about it that way. Just wouldn't have to slow down. So how this
Maybe they just kind of like hit wheels.
How they didn't crash? They just bumped into each other.
Well, then the answer would be they bumped into each other then.
But they didn't. It just ran past each other.
So how can you have to figure out how can you be on a bike and be in the same place at the same time?
This isn't the y-axis, then they're at the same distance from where they were before, but they're not at the exact same place.
I'm saying, like, see, we're at the same distance right now. It doesn't matter about all the directions.
But are you, if you're looking at the graph, when people look at where the lines intersect, how can you argue that being next to each other is the same position?
Because it's the same distance, they're not the exact same place.
So how can you prove that? Can you use math to prove it? Can you use the lab to prove it? Think about how you can prove it. Look back.
No, it's not. It's the same position.
How do we identify the position?
No wait, that's one dimension, the other one.
So that's not the same position. Is that the same position?
Wait.
Different. Even if it's like 5 centimeters, it's still different.
Well, okay.
So there's a bridge.
It's not.
No. It just jumps over.
There's a line. What is this line?
Because it's a starting line. What did this both come out?
Okay, where did you get the starting line from? Are you making things up? This is the
You said there was a bridge, okay?
Wait, this is not on the graph. This is just a picture.
This is a picture.
This is not related to the graph.
I understand.
Yes.
Okay.
So let's say 1 second. And if you look at it this way, goes the same way. So this is the origin.
Does the origin have to be like if you're being
If you're thinking about an origin and region, does it have to be a dot?
like the bicycle? Or wouldn't a starting line
Well,
be a line and not a line?
isn't the origin a point of reference?
Any day.
So you can define, so you're saying the origin isn't a dot, it's a starting line.
So if it's a line, then it doesn't matter. There could still be a bridge.
Or there could be a bridge.
It's not a bridge. It is not a bridge.
How do you know?
Because that's
You're saying they're the starting line.
Because if they're both in the same line, then both of them are gonna go over the bridge and crash on the bridge.
No, it's just like
Listen to Jason,
it's a
take this.
special.
How does your bridge work?
No, actually, it just jumps over.
Oh, he jumps! He's like a,
Jumps and the lines are different.
why would the line be different?
There's no gravity. It's so simple.
If there's no gravity, how would he come back down?
He does it.
That's even more. I'm so lost.
You're just making him look.
So we have to agree upon an answer. We have to come up with an answer.
Okay.
No.
It's 2 to 2.
No, they just.
Why do you?
No, they just crash into each other.
No, because it's
And
two
then-
beats.
Well, you have to convince him why
Oh,
is crashing
no.
into each other wrong.
No, wait. If they crash into each other, then this line.
Because then they
line
can keep
is-
going on.
No, this is the line for B. This is the line for A. They're just like this.
Look, Jason, if
And then
they
they
crash,
bounce off of each
if
other.
they crash, the line would
They crash and then bounce
line for
off.
A wouldn't go over here, and the line for B.
So your argument to Jason is, what is your question to Jason? What question could you ask? How?
How old are you?
Yeah. How? How would the lines keep going on if they crash?
I don't know. I'm just thinking.
But the lines do go on, so that shows that they didn't crash.
Well, you see, they bounced off of each other. It changed, right?
But that means colors.
But this is A, and this is B. Clap once. If you can hear me, clap twice. All right, ladies and gentlemen, I believe you have come to a conclusion in your small group. So what I would like you to please do is to take your whiteboard, put your markers and erasers away, and move our tables so that we can get on our giant group circle. Go. Move your notebooks out of the way, too.
Just
Rule number 1, no side conversations. Rule number 2, raise your hand to talk. And rule number 3, you have to ask a question or answer a question that was asked of you. Check the boards before you raise your hand. So take a second to read first. All right, Anthony.
So, Amy's board. You think they cross?
Yeah.
Why?
Because that's their graph showing. And there's like no other way that they could be at the same place at the same time without crashing.
I thought.
So is it a question?
Sorry. No, I mean.
Oh, you want to make it a question?
Yeah.
Okay.
I thought the graph is like how fast they're going, like the steeper they are. Not the path, right? Or is it the path? I don't know.
What's your question?
He's saying is the
Are you
graph.
saying is the graph the path?
Yeah, it's the graph.
Is the graph, does the graph show the path? This is question.
I mean, it kind of it shows that they like meet at the same place, at the same time. They couldn't do that without having a bridge or something.
More. Explain F or 2 for you.
You could ask her in Spanish, she can respond in Spanish, and then you can translate for her.
Translation.
Go for it.
¿Quieres decir algo de número 2? Lo que sea. No sabes.
Tell her in Spanish. We're all listening. Can't hear you.
Uh-huh. Uh-huh. Is that your answer? Alright,
What'd she say?
She said A and B
Uh-huh.
are not touching each other so they can't crash.
Okay.
That's it.
Will you ask her how are they not touching each other?
Porque no están tocando.
Like on top? Or like next to each other? Like how do they not touch?
Porque no se me tocan.
In Spanish now. What?
Porque no tocan y no chocan. Because she said someone's on top and someone's at the bottom.
Okay. All right, what's your question? Dahlia.
Why do you think it's to be? Because they would have the same position, but they wouldn't have the same velocity.
Lizinski.
Ellie, how can you prove that two things can be the same thing at the same time?
Oh, good question.
Okay, well, if you imagine two people and, well, you can imagine the bikes. Like, they're going like this. One is going at a more uphill and then one's going, like, more that way. Imagine, like, two things can't be in the exact same place. Like, just think about it. Can two people be standing in the exact same place at the same time? Like, no, because...
Yeah.
How? Like
two people standing
so the exact same place, like the actual exact, because those lines, like, they're both in the exact same place. They're not next to each other. They're in the, like, the same.
Joshua.
You said going uphill. How do you know that?
That's just what we think.
Okay.
Izzy.
Couldn't the people be like on top of each other?
Yeah, that's what we said. We said that.
So then your argument is if I had like something on my shoulders, we would be in the exact same place at the exact same time.
Yeah.
Okay. And you can't. And your argument, I'm understanding, is you can't do that on a bike. Okay. Carl.
How can you be the exact same place at the exact same time if you have somebody on your shoulders? That means that they're like not equally level with you. That means they're above you.
Okay, that's not what we said, though. We didn't say that they were on their shoulders. We said that one was on a bridge ahead. And if they were lined up perfectly, they would be.
Well, yes, but like I said, they're not on the same elevation. They're not in the exact same place.
I mean, when I think about it, they would line up perfectly though. So on the graph, if it was like an overhead view, you would see them lined up perfectly, like it was on here.
Aaron?
How can you prove they're at different elevations?
Well, kind of what I said before, like they can't be passing each other because they wouldn't be in the exact same position. That's the only way, is if you saw it like from above view and you saw them, one on the ground level and one ahead or below.
You were like arguing, so are you guys saying there's a bridge, or are they going in a parallel path?
Well, personally, I think they're going in a parallel path, and so I think B is getting a head start, and it's going slower, and it goes faster. And once they're at the same point right here, that's where they intersect on the graph.
Yeah, because it says it in here.
Yeah.
But, and then Lewis, you're on the bridge. You're on the bridge. Okay, and what about you, Aiden?
Parallel.
Parallel. Okay, so I think we have two main ideas. Correct me if I'm wrong. We have the idea that they're going parallel to each other, and it's kind of like this, like Arden just showed us. Or the idea that they go some variation like this, but that there has to be something that puts A on top of B or B on top of A so that they can be in the same position at the same time. Would you agree? Okay, I want everybody to think about which side they're on. Think in your head, which side am I on? All by yourself. You don't have to discuss. Or drop your board. It's okay. All right, now. We've asked a lot of questions. I want you to think in your head, is there anything we could do to prove it? Is there anything that you could do or a question you could ask that would prove once and for all to get us all to success today that your answer is right versus the other answer? Getting attacked here. What do you think, Arden?
What if we could use some of the cars that we used in one of the other labs?
So what do you mean by use the cars?
So maybe we could kind of like almost chart it, like what they're doing, like use a faster car that's one of the faster cars, so that could be used as A, and then you could use a slower car that could be used as B, and then put them in a parallel line, and then have B be put at a little bit faster start, and then see when they kind of, yeah, and then kind of like chart it, I guess.
But how would we solve the bridge? Like, how would we do that?
I don't know for the bridge.
So if we tried the parallel lines, what you want to do is you want to use the car, let me make sure I get this right. So you want to use the car as a fast and a slow car, and you want to see if we get this graph.
Yeah.
With the motion detector things, or what? Or like,
I'm not sure for that part.
What do you think?
We can, with the motion detector thing, we did that lab,
Uh-huh.
we had to walk and get the slope.
So you think we could use her idea with the cars and use the motion detectors and see if we get this graph? Yeah. Would that give us a final answer?
Yeah.
Okay, let's try. So if we do this and the lines cross and they don't crash, then we will know that the lane theory is correct. Am I right? Will we have reached success if we can see that on the screen? Yes. All right, are we ready? On your mark. I'm excited. Get set. Go. All right, do we have data to prove it?
No. Yes, our Honda Accord.
Was there, gentlemen, was there a bridge?
No.
No. So when we have two things that are in the same spot, when they're in when they're in the same spot on a graph, what is that actually telling you about the car? What is it actually telling you about the car?
They're changed. One's passing the other.
One's passing the other, and what is it actually measuring? You are correct. Well, yes,
They're
the
distance.
slope tells you the speed, but what is that spot? If I follow my finger over, what is that spot telling me?
Position.
Yes, so if this is our origin, it's telling me they are the same distance from the origin. All right, ladies and gentlemen, I would like you to find your unit organizer on constant velocity. We started filling in our unit organizer, but we have not finished. So, since we've come to a group class consensus and we all agree, we need to make sure that we have this filled in our notebooks so we can go back to refer to it. Does everybody have their unit organizer out? So mine's blank. but I think we already have some of this filled in. Did we fill in this first section? We filled in this part?
Yeah.
And did we fill in the calculations? We did that? So we just have to do graphs, correct? All right, so motion can be shown on graphs where the slope tells us blank or blank. Let me know, what do we have? Speed or velocity. Which one? And then, so we got, velocity, and then speed, and we're writing this in. And then what do we put down here? It says speed, which does not include, and velocity, which does include. Direction. Very good. All right, so right here where it says graphs, this is what we've just been talking about. All these details on what a position versus time graph looks like. So in each one of these boxes, you can label them time, position, time, position, time, position. At your table, I want you to take a second and discuss what would each graph look like. Ready, set, go. So how do you know it's negative towards the origin?
Moving back towards the origin.
Okay, so its position is changing in the negative direction? Yeah. Okay, very good. What are you doing? The dance? Slope dance? Okay, so how does the slope dance help you?
Slope dance.
It's negative. Not moving.
This is the
And
best
then
slope,
positive.
guys.
Okay,
Going
alright, so
this
slope
direction.
dance. Alright, very good.
Backwards in time.
You ready? Alright, finish conversation. 5, 4, I think we're ready. 3, 2, 1. Alright, what do we put here? Graphs toward the origin. What does that look like? How do we see that? Soria.
It's kind of starting higher and it's going downwards towards the outside.
Like this?
Yeah.
Alright, how about graphs where we're not moving? Sagrika. Straight line going across. What's the slope? 0. Very good, 0. And how about away from the origin? What does our slope meter look like? Positive. And if you want, you could be advanced, and you could label 1 what and 1 what. What does a steeper slope mean? It's going faster. So you could label 1 fast and 1 slow. All right, how do we feel about this? Yes, Catherine?
Can we draw the graph that we just did?
Sure. All right. So we can also draw, well, I'm going to put it up here. I think you have room on the bottom. All right, we'll put a graph that we just did. A, B, position, and time. And what do you want to add in about the graph that we just did? That we just talked about? What do you want to put in there? Okay, so we can put a little dot there, and we could say, you want to say side by side? Side by side. Do you want to write not crashing, no bridge? Okay. Awesome. So now that we have our unit organizer filled out, let's go back to what we talked about at the beginning of class and see if we have reached success. So question number 1, do we all agree?
Yes.
We all agree. Can you say that you're confident about your answer? Is there anyone, if we were to take a pop quiz right now, and there were 2 questions on the pop quiz, is there anyone that's not confident about what they would answer on that pop quiz? That's what I thought. All right, so what I'd like you to do is turn to your neighbor and confidently tell them what is happening with the velocities at 5 seconds and what is happening with cyclist A and B at 5 seconds. Go.
Okay, so velocity and velocity in the universe.
Thank you for joining us in room 2215, where science comes to life. I hope you enjoyed watching my students take ownership of their learning and become passionate about science. How fortunate for me that I get to see this each and every day.